So, my only announcement is we have the Starboard book signing at Book People tonight at 7 p.m. Nicole and I are on the rides, so if anybody here wants to go there, please let us know before we leave. All right, our speaker today is Claudia Raithel. I'm speaking about Sudoku.
Okay, so I'm going to be talking about Sudoku squares and chromatic polynomials. So this is kind of the title of the paper I was working with. So this talk is heavily based on a paper called Sudoku Squares and Chromatic Polynomials, and it's by Agnes M. Herzberg and M. Ram-Murthy. So we're going to be talking more about than just colorings, and so the title on the flyer was Sudoku Squares and Graphs. So just in case you guys don't know what Sudoku is, this is a Sudoku grid. And when somebody gives you a Sudoku problem, what they're doing is they're giving you a few entered in, I guess, squares in the grid. And what they want you to do is they want you to complete the 9x9 grid such that the rows have 1 through 9 in them, the columns have 1 through 9 in them, and each one of these little subsquares has 1 through 9 in them. So, so just to make sure we all understand, so in this top row, we have a 2, a 7, and an 8 missing, and we want to fill those in. So what do? We look where we put the 2, and we first of all note that we can't put the 2 here, but we could put it here or here. So then we look where we can put the 7. We know we can't put it here or here because there's a 7 there and there. So you put in a 7 in the middle, and then you put the 2 here, and the 8 goes in the corner. And then you use kind of the same process to fill in the columns and the subsquares. So that's what Sudoku is. Do you understand what it is? Okay, cool. Cool. So we're going to be talking about graphs, so we need to know what a coloring is. So I'm told this is an overly technical definition. So a coloring is exactly what it sounds like. I give you a graph and you color the vertices. So for example, this is a 3 coloring of this graph with 3 vertices. This would be a 4 coloring. Sorry, that would still be a 3 coloring. But if I wanted to make this coloring proper, I would have to make it a 4 coloring, because when I say a proper coloring, I mean that no 2 adjacent vertices can have the same color. So both of these vertices are blue. So in order to make it a proper coloring, I'd have to change the color of one of these vertices. And I could still do it with a 3 coloring. I could make this one red. And so now that's a proper coloring. So we can reformulate Sudoku as a problem about finding proper colorings of graphs. Okay, cool. So in order to talk about colorings, we need a graph. So we need to construct this thing which I call the Sudoku Graph, which is going to have 81 vertices. So you're going to put a vertex in each one of the 9x9, each one of the grids. So you have a 9x9 grid, so you have 81 vertices. And then you connect 2 vertices if they're in the same row, if they're in the same column, or if they're in the same subsquare. So let's just count the number of edges just to make sure we're all on the same page. Say I fix this vertex here. Then I connect it to all of the vertices in the top row. That's 8. I connect it to all the vertices in this column. That's another 8. And then I connect it to the 4 vertices in its little subsquare. And I do that for all of the vertices. So in the end, I'm going to have 81 vertices. And for each one of the vertices, I do this process. And so then it's 8 plus 8 plus 4. But then I have to divide by 2, because I'm going to count each edge twice. And that's going to be 810. So we have this huge graph. And we're going to call it S, and it's our Sudoku graph. Cool. So then say I give you a Sudoku problem. So when I say Sudoku problem, what I mean is that I give you an 9x9 grid with a couple of numbers filled in, and you're supposed to complete the grid. So I give you a Sudoku problem, you draw your graph with 81 vertices, and then you assign to each number in the Sudoku grid a color, and you color in the corresponding vertex in the Sudoku graph with that color. And then the question of whether you can complete the Sudoku problem on the left corresponds to if you can find a proper coloring of the Sudoku graph that respects the subcoloring that you've fixed. Does everybody understand that? Okay. So we're going to prove some kind of like what I think are cool theorems using the notion of a partially ordered set. So a partially ordered set is just a set P, and you have a binary relation, which is just called greater than or equal to, which is reflexive and transitive. So what it means to be reflexive means that if I give you x and p, then x is always going to be greater than or equal to x. Transitive means that for y, z, and x in P, if y is greater than or equal to z, and z is greater than or equal to x, then that implies that y is greater than or equal to x. So you guys are already all familiar with partially ordered sets. So for example, the natural numbers, or R, are both posets with just the standard greater than or equal relation. Furthermore, if you have a subgroup, if you have a group and you look at its subgroups, those are partially ordered by containment. The same is true for subspaces of vector spaces, and also the power sets of a set. And so the relation there is always containment. So what we want to do is we want to introduce a poset in our context. So we kind of want to define a new one for our Sudoku graph. Okay. But first, we're going to introduce the idea of a Mobius function associated with the partially ordered set. So this is the definition, and I'm going to write it on the board because it's going to be important and it's easy to forget. So mu of xy is equal to, so mu of xx is always just equal to 1. Okay, and then mu of x comma y is equal to negative the sum over z between x and y, so closed interval at x, open interval at y, mu of x z. Okay, cool. And this is if x is less than y. And the function is 0 otherwise. So, so you'll notice that you don't even need the 0 otherwise, right? Because if x is greater than y, then there's not going to really, this won't really make sense, right? So you need it to be 0 otherwise. Okay, so just to make sure we come to terms with this definition, let's just calculate it once. Let's calculate a Mobius function for the natural numbers with the greater than or equal relation. So if you just fix a natural number n, then mu of nn is just equal to 1. Right, that's by just this first point right here. Then what we want to do is we want to just look at mu n n plus 1. So we know that if we just look at the sum right here, that's going to be from n to n plus 1, and the only possible z is going to be n itself. So that sum is just going to be negative mu of nn. So we go back and we look that, and we see that that's negative 1. So then we look at mu of n comma n plus 2, and so then we look at our sum. We get these two terms, but they cancel, and so we get 0. So in particular, we note that mu of n comma m, where n is less than m and the difference is greater than or equal to 2, is actually going to be 0. And you can prove that just inductively by looking right here. So if we expand out the sum according to the definition, then by your inductive hypothesis, you're going to know that all of these higher order terms, like, so anything like past this plus sign, so mu of n, comma n plus 2 and higher, up to mu of n, comma n minus 1, those are all going to be 0. And your first two terms are going to be 1 and negative 1, and they're going to cancel. So that's just going to be 0. So we've calculated the Mobius function now. It's going to be, so just to write it concretely, so mu of nm is going to be equal to negative 1, oh sorry, 1 if n equals m, minus 1 if m equals m plus 1, and 0 otherwise. So it's actually like pretty simple. So does everybody understand this calculation? Okay, cool. Okay, so then we have this theorem, which the paper didn't really call Mobius inversion, but I think it usually goes by the name Mobius inversion. So if you have a function, from your poset into C, and you define g of y is equal to this sum, then you know that f of y is just going to be equal to that sum. So just to get a handle on the theorem a little bit, I thought we would work through another example, just to be happy about it. So say that I just tell you that f of x is equal to x plus 1. So then if we let g of y, so let g of y be equal to the sum, so x less than or equal to y, f of x, which is just going to be the sum okay. So if you add, oh sorry, and this is the poset we're working with is the natural numbers here. So I'm summing over all natural numbers less than or equal to y. So if you remember, the sum of all the natural numbers up to a certain point is just going to be y times y plus 1 over 2. Okay, and then you add the 1 y times, so this is going to be plus y. Okay, so g of y is really just equal to this. And so then we want to figure out our f of y. So I'll erase this. So then f of y is going to be equal to the sum of x less than or equal to y, mu of xy, g of x. Okay. But we just calculated this Mobius function. There's only two non-zero terms. The case where x is equal to y and the case where x is equal to y minus 1. So when x is equal to y, we get a plus 1 term. And so that's going to be equal to just g of y. When x is equal to negative 1, we get that the Mobius function is negative 1. So that's going to be minus g of y minus 1. And then if you just plug in y and y minus 1 into into g, and you just work that out, you figure out exactly that f of y is just going to be equal to y plus 1. So I hope that kind of like makes it not seem like gibberish. But so we're going to use this theorem. Okay. So now we want to actually talk about the poset that we're going to be talking about. In order to do that, we need to talk about what a contraction in a graph is. So to contract a graph along an edge E means that you're going to be identifying the two vertices joined by that edge, and you're going to then identify any resulting multiple edges. So for example, here we contract along the edge E, then we get these multiple edges, we identify them, and then we eventually get this graph. Okay. Okay. So the poset that we're going to be talking about is going to be different for every Sudoku problem. So the allowed operations are that you can contract an edge in your Sudoku graph as long as one of its vertices lies outside of the predetermined coloring. So when I give you a Sudoku problem, you go to your Sudoku graph, you fill in your coloring corresponding to the numbers that were in the graph that I gave you, and then you can contract any edge as long as it has one vertex outside of that predetermined set. So we say that S prime is less than or equal to S if S prime can be obtained by contracting edges in this way from S. And this is a partial ordering on that set of graphs. Okay, cool. So once again, just to make sure we understand everything, I thought that we would calculate a couple of examples. So let's look at this graph right here. I think this is like the Big Dipper or something. Maybe like flipped. Okay. Okay. So say this is a graph, and I'm just going to give you a couple of vertices, and I'm going to tell you, okay, this is how you color those vertices. So I'm going to tell you how to color these 4 vertices. Then say this is, so this graph right here, this rectangle, we're just going to call that S. And the entire graph we're just going to call G. And then what I want you to do is I want you to calculate mu of SG. Okay, so how would we do that? The first thing to notice is that there are a couple of graphs that are between S and G. So what can we do? We can contract this edge, and that gives us this graph. We can contract this edge, and that gives us this graph again. And we can contract both, and that just gives us back S. Okay. So the Mobius function of SG is going to be negative the sum of the Mobius functions mu of S G prime, where G prime varies over these 3 graphs. So mu of SS is just 1 again by definition. And then notice that for any one of these 2 graphs, you can get from this graph to S by just 1 contraction. So if you go back to the definition of the Mobius function, you're only going to have 1 term in the sum for the Mobius functions of these 2 graphs. So if this is G double prime, we want to look at mu of S G double prime. And it's just going to be that recursive sum defined over there. But you're going to only have 1 member in that sum, because the only graph between S and G double prime is S itself. And so this is actually just going to be -1. And so each of these 2 graphs contributes a -1. This contributes a +1. So if we add that, we get a -1. But then we negate it according to our definition, and we just get a 1. So mu of SG prime is 1. Okay? So let's look at one more. Let's look at this graph. So once again, let S be your predetermined graph, and let G be the entire graph. So do you guys want to show me how to calculate this Mobius function? Like, what do you think we should do first? We should determine the intermediate graphs, right? Okay. And how do we do that? We do that by contracting edges. So if I contract this edge, then I'm going to get, okay, so I'm going to just label the edges here. Okay. So contracting E leads to my Big Dipper guy again. Okay. Contracting D also leads to my Big Dipper guy again. Contracting F, same thing. Okay. And then if I contract, say, D and F, then I get back to S. So then I get, so D and F, get back to S. And then if I contract E and F, I also get back to S. And we just, and then if I can, yeah, OK, those are the only two. OK, and so then we would get 3 contributions of -1, 2 positive ones. That would give us a -1. We would negate it, and it would be 1. So that's how we would calculate our Mobius function in this scenario. OK, cool. OK, so this is the theorem that actually I thought was really cool. So we have our Sudoku graph S, and it's a finite graph, and it has V vertices. So this is actually a little bit more general than just the Sudoku graph. So in our case, V would be 81. But so let's just say that S is a finite graph, and it has V vertices, and C is a partial proper coloring of that graph. So that would correspond to the partial proper coloring that you would fix when I give you your Sudoku problem. And this partial coloring, you color T vertices, and you use D naught colors. Then the number of ways that you can complete this coloring to a proper coloring of the entire graph is going to be given as a polynomial in lambda, where lambda is the number of colors you're using, with integer coefficients and degree v minus t. And this is just for lambda greater than or equal to d naught. Actually, this is a monic polynomial, so we'll actually show that in the end too. OK, this is actually not too hard. So say that you have, so if you just look at your big graph, which I think I've accidentally renamed G on the slide. So look at your big graph G, and say that I hand you just any coloring, not necessarily proper, that respects the subcoloring that you fixed. And I'm going to tell you that you should contract edges if the 2 vertices that they connect are of the same color. So if you go through this process, what you're going to do is eventually you're going to get a proper lambda coloring of another member of the poset, and it's going to be unique. So each coloring of G corresponds to a unique proper lambda coloring of G prime. And conversely, if I give you a proper lambda coloring of G prime, you got to G prime through a series of contractions from G. And so you can make a coloring on G that would go through the same series of contractions and get to your coloring on G prime. So actually what you find is that there's actually a bijection between lambda colorings of G that are not necessarily proper and proper lambda colorings of G prime, where G prime are just other members of the posets. And so then we think about, OK, how many lambda colorings are there of G that respect the coloring on the subgraph? It's just going to be lambda to the v minus t, because if I have lambda colors, each vertex can be one of those lambda colors. I have v minus t vertices, so that's just going to be lambda to the v minus t. And because of the bijection that we have, we know that this is equal to the sum over members of the poset of number of proper lambda colorings that respect C. OK, so this is where we use Mobius inversion, right? Now we've set ourselves up to use it. OK, cool. So then if we just apply Mobius inversion, we get that. So this is actually, there's actually a typo on this slide. We actually get that P of GC of lambda is equal to you sum over the members of the poset mu of G prime G lambda to the v prime minus t. And that typo confused me for a really long time. And so we get that the number of ways to complete a proper subcoloring with lambda colors is just this polynomial. where this is the Mobius function associated to our poset. So we want to show that this is, so it clearly has integer coefficients because the Mobius function only takes integer values. So we want to show it's monic. So what's the highest order term here? What would that correspond to? That would just be, in order to get the highest order term here, we would want to maximize v prime. V prime is the number of vertices in G prime. The maximal element of your poset is the big graph, which has v vertices. So the highest order term here would be mu of G lambda of v minus t. And this is just 1. So you have a monic polynomial and the number of colorings that the number of colors you're using. So I thought that was really cool. And so this is actually, so the reason that the author of this paper was talking about chromatic polynomials is, so when I give you a graph, a chromatic polynomial it's a polynomial in lambda, where lambda is a number of colors. And I plug in lambda into the polynomial and it spits out the number of proper colorings that it can give me. So that's what a chromatic polynomial is. And so this is kind of not exactly a chromatic polynomial because you're also respecting a subgraph. Okay. So what does this say about Sudoku? So there's something really obvious that this actually reproves. So say that I give you a Sudoku and we think of it in this graph framework, and the predetermined graph that you get color has less than 7 colors. So this would correspond to if I give you a Sudoku graph, and in the entries that were in the Sudoku graph to begin with, you just use numbers like 1 through 7. And I completely left out 8 and 9. So say that you found a solution of this Sudoku. Well, that solution can't be unique, right? Because to get another solution of the Sudoku, I could just switch 8 and 9 in my solution. And so you have at least 2 solutions right away. So observing that the solution is unique for d naught less than or equal to 7 is really not wonderful, but it's kind of cool. And so the way that we can see it from this polynomial that we've derived is that we know that the number of ways to complete a coloring, so I forgot to say, the chromatic number of a Sudoku graph is at least 9, right? You can't color a Sudoku graph with less than 9 colors because for every vertex, you're attached to already 9 guys in this, 8 guys in one row, and so you need 1 color for each one of those vertices. So you need at least 9 colors. So you know that the polynomial that we just derived evaluated from d naught up to 8, it's going to have to be equal to 0 because there are no ways to complete that coloring with less than 9 colors. So then we can factor the polynomial like this, where q has integer coefficients, and then we plug in 9, and we get this. And when d naught is less than or equal to 7, that's going to be greater than or equal to 2. And it has to be positive because we're counting the ways to complete proper colorings. Okay,
is
cool.
Is that factorial or?
Yeah, it's a factorial.
Okay. I've got bad eyes.
Yeah. Yeah, it is. Actually, now I'm wondering if it should be.
It is for lambda equals 9.
What?
It is for lambda equals 9, right?
Yeah.
The last term will be 1.
Okay, yeah, you're right. Thank you. Good, thanks. Okay, cool. So now we're kind of going to shift gears into the second topic. So the last thing I wanted to observe about the uniqueness of Sudoku solutions is just this trivial observation. If you have this 9x9 Sudoku grid and you have a solution if you have this subsquare right here and you have 9, 4, 4, 9, and they're across the boundary of this subsquare, then you can just switch the 4s and the 9s, and you're going to get a solution again. Because you're still going to have 1 through 9 in this square, you're still going to have 1 through 9 in this square. You're not going to mess up the rows because you're switching. For every 4 that you take up here, there's another 4 coming down. And vice versa for the 9s. And you're also not going to like screw with the columns because I take away a 4, I put back a 4. So if you have anything like this appearing in a solution, it's also not unique. Cool. So another interesting question that the author of the paper talked about was you have this notion of a Latin square, which came before Sudoku squares. And a Latin square is just like a Sudoku square, except you don't have the subsquare condition. So instead of having 1 through 9 in every row, column, and subsquare, you just have 1 through 9 in every row and column. So on the left, and then we have this notion of rank and order. So a Sudoku puzzle or Sudoku square of rank n is just going to have n by n subsquares. So the normal Sudoku squares we look at are of rank 3 because our subsquares have 9 entries. But so a Latin square is going to be, so that Latin square on the left is of order 4. So you just count the dimension. And so an interesting question that you can ask is every Latin square of order n squared a Sudoku square of rank n? And if not, what's the probability that a Latin square will be a Sudoku square? Cool. Okay, so I also thought that we should also just talk about the existence of a rank n Sudoku. So there's an easy way to prove that there exists a rank n Sudoku. If you just, so if I want a Sudoku of rank n, what I'm going to do is, to fill it out, I'm going to do it in bands of n. So I'm going to start with 1, n plus 1, and then I'm going to go all the way down to, and I'm going to complete this row all the way out to n squared. And I'm going to complete this row to n squared, and once I reach n squared, I'm going to start over at 1 again and go to n. And do this for all of the rows until I go to n minus 1 times n plus 1. Okay, so this is the first n band in the Sudoku square. Okay, then what I do is I start at 2, and I go out to n squared, and then I add a 1 at the end, and then I do n plus 2, and I go to n squared, and then 1, and all the way to n plus 1, and then I go all the way down to n minus 1. Yeah. Wow, what did I do? Oh, sorry. Okay, yeah, n minus 1, n plus 2, and then I do the same thing here, and I just keep doing this. So this is the second band of n, and I just keep doing this until the last band is going to look like n, and I'm going to complete the row in the way that I've talked about above, and then it's going to start. You're going to start at 2n all the way to n squared, and this is going to give you an n by a rank n Sudoku square. So how can you see that? Well, your row condition is obviously satisfied because you've entered 1 through n squared on purpose. Your column condition is also going to be satisfied. So notice that the difference between this entry and this entry is always just going to be 1 mod n squared. And so if we can show it for this column, we've shown it for all the columns. So here, 1, 2, and then we would have 3, 4, all the way to n. Then we would go here, n plus 1, n plus 2, and we would go all the way to 2n. Then we would start here, and it would be 3n plus 1. Then there would be 3n plus 2 in this band, and we would just go down that way. So the columns all have 1 through n squared in them as well. So then if we look at if we look at a subsquare, so a subsquare would cut this span off at n. So you would have 1 through n in this row. Then you would have n plus 1 to 2n right here. Then you would start down here, and it would be 2n plus 1 through 3n. It would be 3n plus 1 to 4n. And so that's how you satisfy the subsquare condition. So you do have, for every n, a rank n Sudoku square. And I've filled in an example for you for the rank 3. So this is the generic way of filling in a rank n Sudoku. OK, cool. So in proving that we have a rank n Sudoku square, we've also shown that there exist order n squared Latin squares. Because every rank n Sudoku square is an order n squared Latin square. And so you can ask the question we've already asked. So is every Latin square of order n squared a rank n Sudoku? And the quick answer is no. So these guys named Fedenhauer and Yavis calculated that there are that many valid rank 3 Sudoku squares, and I don't know how to say that number. And you have that insanely huge number of order 9 Latin squares. So a very small number of Latin squares are actually Sudoku squares. Cool. But we can actually, so as n goes to infinity, we can actually get a much better answer to the question of how many Sudoku squares are actually, how many Latin squares are actually Sudoku squares. So, and in order to do that, we're going to do more technical stuff. So we're going to define the permanent of an n by n matrix. So the permanent, if you look at it, the formula for it looks a lot like, I just broke my earring. looks a lot like the formula for the determinant, except you're missing the sign in the sum that corresponds to the order of the permutation. So I think the best way to understand what this definition is saying, we really just have to do an example. So let's just look at the 2 by 2 matrix A, B, C, D. OK, this is a 2 by 2 matrix. So we're going to be summing over permutations in S2. So there's only 2 permutations in S2. There's the identity, and there's the transposition. 1 goes to 2, 2 goes to 1. So let's look at our sum. So the term corresponding to the identity, you're going to take, OK, so A1 sigma 1, what is that? That's going to be, you know that you're in the row 1. And when you apply sigma to 1, so if this is sigma, you're still going to have 1. So A1 sigma 1 is just going to be A1 1. So cool. And furthermore, A2 sigma 2 is just going to be A2 2 when sigma is the identity. So the term in that sum corresponding to the identity permutation is just going to be AD here, because this is A1 1 and this is A2 2. So let's go to this permutation. So if this is equal to sigma, then A1 sigma 1, well, sigma takes 1 to 2. So A1 sigma 1 is going to be equal to A1 2, which is B. If you have A2 sigma 2, well, if this is sigma, then 2 goes to 1. And so you're going to have A2 1, which is C. So this is the permanent of a 2 by 2 matrix. And it looks a lot like the determinant, right? The only thing that was missing was whether we considered if they were odd or even permutations. So a matrix is called doubly stochastic if the sum of the entries in each row and each column are all equal to 1. So for example, the identity is double stochastic, because if I sum any row, it's equal to 1. If I sum any column, it's equal to 1. If I sum any row, it's equal to 1. And then I think in the 1920s, they came up with this conjecture. They wanted to minimize the permanent of an n by n matrix. And they said that the minimum permanent would be attained if each entry of the n by n matrix was just 1 over n. So in the case where we're working with 2 by 2 matrices, they conjectured that the minimum permanent would be attained by this matrix. So just 1/2. And the permanent of this matrix is just given by, okay, so what did we say? We said it was AD plus BC. Okay, and where were my AB? Let's just calculate that. So that's going to be 2 over 4 equals 1/2. Okay, so the permanent of this matrix is 1/2. And so the idea that this kind of matrix, this n by n matrix with 1 over n as entries, gives the minimum permanent, gave rise to this conjecture, which was like proven in the 1980s. And so we're going to use it in giving a lower bound on the number of Latin squares. Okay. So, but before we continue, we have to go through a little bit more formalism. So say I have the set of natural numbers 1 through n, and I give you n subsets of that set of natural numbers. Then a system of distinct representatives is just you grab one element from each set, and those elements better be different if they're coming from different sets. So that's just a system of distinct representatives. And so to each set of sets of integers, you have an associated Hall matrix, and you just define the entries in this way. So Aij is going to be equal to 1 if and only if I is in Aj. And then we have this theorem about the permanent of the Hall matrix. So we'll do an example. So say that I have integers 1 through 3. So I have 1, 2, 3. And I have sets A1 is equal to 1, 2. A2 is equal to 2, 3. And A3 is equal to 1. Okay. So what's the associated Hall matrix? So I want to call my Hall matrix A. And A11 is going to be equal to 1 if and only if 1 is in A1. A12 is going to be equal to 1 if and only if 1 is in A2. And so we continue in this way. So let's write the first row of our matrix. 1 is in A1, so we get a 1 for A11. 1 is not in A2, so that's a 0. 1 is in A3, so that's a 1. Okay. So let's do the same thing for 2. So 2 is in A1, so we get a 1 here. 2 is in A2, so we get a 1 there. 2 is not in A3, so we get a 0 here. Okay. So, and the last row is going to be this, because 3 only shows up in A2. Okay. So then, let's calculate. So then Hall's theorem, the one that we're going to use, states that the permanent of the Hall matrix is going to be exactly the number of systems of distinct representatives that you can get. So here, we know that the only thing you can choose from A3 is 1. You need to choose something different in A1, so you have to choose 2. And then in A2, you have to choose 3. So the permanent of this matrix better be 1. And you can show it's 1. I'm not going to do it, but you would show that it's 1 by just summing over all the permutations in S3. And there's 6 of them, and so you just have to go through that calculation. Cool. Okay. So now we're going to give a lower bound on the number of order n squared Latin squares. And it's that horrible thing that has the e in it. But it's actually like pretty cool to figure out. So say that I give you an order n squared Latin square. Oh, sorry, an n by n Latin square. So then the first row, you can there's n factorial ways to complete the first row. Okay, so then let's think about it. So if I give you a Latin square and I've filled out the first k rows, and you want to fill out the k plus first row. So here's my Latin square, and I've filled out the first k rows. So you have n minus k rows left to fill out. And we want to figure out the number of ways to fill out the k plus first row. Okay. Okay. So then for the ith position in this row, there's a sequence of numbers above it, right? Because you've filled out k rows already. So you collect those entries into a set, which we're going to call AI. Okay. And so for the k plus first row, the k plus first row has n entries, so it has n spots for us to put things. And so we're going to get n of these sets, a1 through an. So then what we can do is we can look at the Hall matrix associated to these matrices. Okay. So say I have a Hall matrix. What does that count? I wrote it down for myself. So we want to claim that this Hall matrix is doubly stochastic. So let's go back to our example. So if I add the entries of a Hall matrix across a row, what it's really counting is if it's the ith row, and I add the entries across the ith row, then what I'm really counting is the number of sets that I is contained in. So for example, in our example, I think I had A1 equal to, I guess, 1, 3. Oh, sorry. So 1 is contained. And then 1, 2. Okay. So these were our sets here. So if you look at it, I'm adding across the first row. And what that really corresponds to is how many sets 1 is contained in. So I know that each row has to contain each entry from 1 to n. So in each row, I have, for any j between 1 and n, I have 1 j showing up. And I have n minus k rows. OK, sorry, I'm sorry. These AIs should have been the guys that are not. So the AIs are not the guys above. They're the guys that are not above. So the AIs are going to have size. I'm sorry, that was my fault. The AIs are going to have size n minus k, because you've used k guys. And so you know that for each j between 1 and n, you know that it's shown up in each row. And so if it's shown up in a row, you know that it's shown up. You know that it doesn't show up in one of the AIs. And so you know that it shows up k times in here. So it doesn't show up n minus k times. So if you add across the rows of the Hall matrix, you're going to get n minus k. And then if you add down the columns in a Hall matrix, you're really just counting the number of elements in the corresponding set. So if I add down this column right here, what that corresponds to is the size of the set A3. So since all of our sets have size n minus k, adding down the column is going to be n minus k. And so, in fact, the Hall matrix, if you pre-multiply by factor 1 over n minus k, is actually a doubly stochastic matrix. And then what we can do is we can apply Hall's theorem, which we talked about on the last slide, which, by the way, was, what was it? Oh. Does anybody remember what it was? Saying exactly what it was. OK. That was it. OK. So according to Hall's theorem, we know that the permanent of a doubly stochastic matrix is greater than or equal to n factorial over n to the n. Okay? And so then, because the Hall matrix that we have is doubly stochastic, once we multiply by this prefactor, we get this inequality. And I don't know why I thought it was a theorem by Bregman, because I don't know who Bregman is. But so you get this inequality. And then, so we've figured out how many ways there are to complete the k plus first row, but we have to do this for all the rows. So we have to take the product for k in 0 to n minus 1, and that yields that the number of Latin squares is going to be at least n factorial times 2 to the n divided by n to the n squared. Okay, so then we have that inequality. So the way to finish it is we apply Stirling's formula. And we recall that Stirling's formula looks like this. And so then if we take e to the log of something, we're really just, x equals e to the log x. So what we do is we just showed that the number of Latin squares is at least that number. And so then we take e to the log of that number. Then we apply Stirling's formula to the first part. We get this. So then if we gather out the big O of n squared log n terms, we get this, which is that, and that's what we wanted. Do you guys want me to go through this calculation? No? No? OK. So you know that the number of Latin squares is bounded below by that. OK, sorry. The number of Latin squares of order n squared. Because we got this result on the last page, right? We got the n factorial to the 2n, and then we plugged in n squared on this slide. And then we applied Stirling's formula to get our result. OK. So then it's harder to show, and I'm not going to bother to do it, that the number of Sudoku squares of rank n is bounded by that equally disgusting looking thing. And for sufficiently large n. So all of this is happening as n is going to infinity. So then we want to talk about the probability that a randomly chosen Latin square is actually a Sudoku square. And we know that the number of Latin squares is at least a, where a is this. We know that the number of Sudoku squares is at most this. So we know that the probability that a Latin square is a Sudoku square is going to be less than or equal to a divided by b, which corresponds exactly to this inequality. And so then you'll notice that as n goes to infinity, the probability that a Latin square is going to be a Sudoku square actually goes to 0. And that's the end of my talk.
Anyone have any questions? Let's thank our speaker again.
Okay, thanks.